Hi, in this video, we want to take a look at three packages that are very useful for geospatial analysis of composition data. All right, so we're going to go over the SP package, which has objects for spatial data, any old data, and we're going to talk about gstat, which provides geospatial statistical tools, and we're going to talk about another one, the one that's connected to the textbook, the gmGeostats package. And that's the one that is specialized for creating a bridge between regular spatial statistics and composition data. So composition data, remember that when I have composition data, for every single observation, all the variables add up to a constant value. Like, for example, let's say I had percentages, then for each observation, every single variable would add up to 100%. Or I could go with fractions where everything adds up to 1, maybe parts per million where everything adds up to 1,000,000. Now, for this to make sense, of course, all of my variable values need to be non-negative, 0 or positive. And we're going to be working through some information from Geostatistics for Composition Data with R, Chapter 4. Here are the names of the authors. And we're going to be using some help documentation from the SP package. University of Central Florida students can download the textbook for free through the library. Here is the CRAN page for gmGeostats. Here is the CRAN page for the compositions package. And here is the professional website of one of the authors. All right. So now let's start talking about it. So we've got the SP package, the gstat package, and we have the gmGeostats package, are the ones that we're going to focus on here. Also, the compositions package is one that is going to be very important to us when we're doing this type of analysis, but those packages have already been looked at in chapters 2 and 3. Now we're transitioning from composition data into spatial analysis. And so right now we're just thinking about spatial analysis in general without considering the fact that our data is composition data. Okay, so the SP package, this provides objects, classes for us to store our spatial data in. And so this could just be coordinates, or this could be coordinates with corresponding data. Now the gstat package, this provides tools for geostatistical analysis after I have my geostatistical data in an object that I can work with, usually the SP package. And gmGeostats, this is specialized for composition data, and this is a bridge between the multivariate composition data with spatial data analysis. Now, the composition package is also super important for us, but that is just on its own tailored for multivariate composition data analysis without considering geostatistics. All right, so let's talk about the SP package. So the SP package provides a whole bunch of objects for us to store our data in when it is spatial statistics data. And so we can have several different topologies going on. If you go into my YouTube videos on geospatial analysis, the spatial data analysis videos, I go over this package a lot. And so if you're interested in it, please bounce over there. A lot of good stuff going on in there. And so we can have different topologies for our GIS data. We can have either vector-based or raster-based GIS. For me personally, professionally, everything I've done has been vector-based. I've never actually done anything professionally with raster-based GIS. The vector-based ones, we can have locations, like points on the ground, lines, for like a river, or we can have polygons for counties, states, countries, something, anything like that. For raster-based GIS, we can have grids or pixels. And the few times I have touched on rasters personally, I've been working with the pixels. All right, so here's just an overview of the different classes that we can have in the SP package. And I believe, there are other ones, but these are the ones that are listed in the vignette for the SP package. And so we can either have like points on the ground where I know the coordinates, and that by itself will be stored in a spatial points object. Now, this won't have any data with it, and this is going to just be like spatial data. Now, if for each location I want to have associated data inside the object, then I'm going to take the spatial points object, but I'm going to have a data frame on there. And so, yeah, this data frame should be over there. That's a mistake. And so we'll have spatial points and we'll have a data frame inside this object. And so this is how we usually associate observations with points on the ground. Now we can also have multi-points. And so this will be in a spatial multi-points object. Now here we won't have associated data, and everything is just spatial. Now, if I want to associate data, I need to extend this class to its name with data frame on there. And I'm going to have a data frame in there for the association. And so it'll contain spatial multi-points on there. For pixels, I'm going to have spatial pixels. You're going to see a theme throughout these names. Now, I can't have any data, and we're going to have spatial points for our pixels. If I want to associate data to each individual pixel, then I'm going to need to have a data frame with spatial pixels, connected to the data frame. And so, we have our spatial pixels and we have our spatial pixels data frame. And, if I want a full grid of points, so this is a special class of spatial points. If the spatial points form a grid, then it's a spatial grid. And, everything works out pretty much the way you would expect it to go. And we end up getting a spatial grid data frame if I want to associate data points to each point on the ground. Now we can have a line, which will be in a line object, or we can have lines, plural, in lines object. And they are different. There's some nuance in there where here for lines, I'm going to have a list of line objects. And so we can have also spatial lines, slightly different, but similar objects. And we can have, for our lines, we could also have a spatial lines data frame. And in this situation, I would be having a data point for each individual line. So imagine I have like rivers or roads, and I want to connect data of like, if it's roads, how many deaths per year do we have on each of the roads? We also have polygons, which what's going to end up happening, well, there's a couple of different ways to go about this, but one of them is when I have a polygon, I'm going to have I'm going to have a line, and I'm going to say, hey, these go and these connect together. And we can also have multiple polygons, and then in that situation, we could have a list of the polygons here. And we can also have spatial polygons. And you'll notice I don't have any data associated with any of these. I don't have any data associated with any of these. If I want to have data connected to individual objects, I need to make sure that I have data frame in the object's name. And this is important when either we receive an object that's from the SP package and we work with it, or I need to build it manually myself. So kind of like the situation where I have like a data frame that includes a whole bunch of data. I have a key to match to coordinates of or to match to a spatial object, and then I have the actual coordinates involved, whether that's a line, a polygon, like a state, or a grid or whatever it is. I have I have a connection going across, and so then I'll have two objects floating around within the SP object. All right, so spatial points, these are locations in space. Spatial points data frame, this is spatial points that have data associated with each location on the ground. Now, spatial grid, so this is a fully regular set of points, of spatial points. And if I have spatial grid data frame, then really this just is just specifying that my spatial points are a fully regular set of points, and the relationship between the data and the points is the same. Now for spatial pixels, this contains just a subset of locations on a rectangular grid, and the spatial pixels data frame has data associated with each point on the grid. In all of these three cases, the number of points of a set must correspond to the number of rows of the associated data. All right, so what this is saying is that every time I have a spatial object, whether that's a point on the ground or a line or a polygon, each one of those, I need to have an associated row in my data frame for it to be a spatial data frame, and for the system to work correctly. A huge problem for us when I'm working with data is if I have a pre-established spatial data frame and then I want to join in some new data. You can really screw up your data if you don't use the right merge or join function on this. And so be warned about that. I have made that mistake. I actually made that mistake this week, and I had to go back and correct it. So be warned, be aware of it. It's an issue. All right, a spatial grid can be created with a specification of a grid topology by means of the function grid topology, which requires the coordinates of the upper left top cell and the cell size and the number of cells on each direction. And so here is an example of it, is the grid topology. Now, when I say topology, I mean this in the most baby sense possible. Don't think of the analysis of open sets. This is far simpler than that. This is not a pure math class. It breaks my heart that I'm using the word topology, and I'm not talking about open sets or compact sets or anything like that. But here we are. So here, we say the dimensions of our cells. We say our cell center and offset, and we talk about our cell size. And it will go through, and just generate all the points on the ground if I use this. And if I need to, I can go through and start mapping things and stuff like that. Also, something as a major consideration, if I start joining data sets, I need to consider what, not just the combining of data on the data frame, but also if I'm combining two spatial data sets, what happens in the geographic aspect of the spatial data? I've got all that in my videos. Good stuff to dig into. So the data set contained in an object of class spatial data frame can be extracted using the syntax of slot object and then data. Okay, and so the spatial coordinates of a location can be extracted using the syntax coordinates object. And so what I'm saying here is if I have a spatial data frame and I want the data, I just name the object and I put into quotes data, and that'll give me the data frame back. I can also use as.data frame. That's another way to go about it. The slot method is the way that the author of the textbook talks about. I usually use as.data frame just because I use as.data frame a lot in my work. Now, if I want the coordinates, I just use the coordinates function in SP. And so here I'm loading my data, and so this is a spatial points data frame. It's actually a grid of points, but it's not stored that way. And so now I've got the object, and if I want to get the data, I just put both of those into the slot function, and it'll extract it for me. Now, if I want the coordinates, then I'll use the coordinates function. And I can actually call these in multiple ways, depending on what your preference is. I've never noticed a meaningful difference between the different methods, but you can do it however works for you. And so here we can see the coordinates. Now, my first chunk of code was to round off the digits, and you can notice that these are all the same because of rounding. And if I look at the actual data set, I'll notice that if I don't round off, there are differences between these coordinates. Now, to see what's going on with the individual object, like what the slots are and what's contained in there, I can use the str function, and it will go through and it'll print all of the different slots for me. Str stands for structure, and so you can see we have a spatial points data frame. It's from the SP package. It has 5 slots: data, coordinates, NRS, coordinates, bounding box, and its projection. And so here, if I want to pull anything out, I can actually use these names to get what I want out of there. All right, so that finishes up our very brief look at the SP package. Now let's take a look at the gstat package. All right, so here, this is a package that's designed for analysis of spatial data. So I want to run spatial statistics on what's going on. And so I want to do statistical modeling. So this is more than just drawing a map. I want to actually have a mathematical statistics model going on, not just a picture. So this is where we start to see like R and Python diverge in terms of utility. Python does great for maps, but really this isn't 100% true, but morally speaking, compared to what the features in R, Python just stops at maps, and that's it in terms of spatial analysis. R takes it to a degree that you don't even know about until you start peeling back the layers of that onion. So R for spatial statistics is just vastly better than Python, just because there's just more interest in that, because of like the scientists that use R. In the science lane, usually R is more popular than Python. In industry, Python is far more useful. I shouldn't say useful, used more. It's just more popular because of who's running, IT departments, basically. So if you're going to learn one, honestly, learn Python for employment. It's a better choice. But R is more beautiful. So the gstat package comprises like variogram calculations, where we're going to take into consideration a spatial aspect of the variance of what's happening, and statistical modeling and computation of estimates and simulated realizations of our data on a defined grid. Spatial data are specified as a gstat object by defining the name, the object, the variables to be modeled, the coordinates, the calculation parameters for the variogram, and associated models, along with the relationship between the data and the coordinates of the grid. All right, there's a lot there. We'll dig into this more later. In my other videos, I use gstat a lot in those videos. So let's do some further estimation and simulation details. Further estimation and simulation details need to be specified as you go through. So you have a lot of options. There's a lot to wade through when I'm using this package. Let's run through some examples. This is modified from the help documentation for the variogram function. All right, so here I'm going to load the MeUse data set. And in this data set, it has an X and Y coordinates in the data frame itself. And so as is, it's just a data frame just floating around. It's not actually ready to be used. So I need to tell R that, hey, you have coordinates in this data frame, go get them. And so here, coordinates, same coordinates I used a moment ago for extracting. Now I'm using the coordinates function for assignment. I'm assigning X and Y to be the coordinates of the data. And notice this, I have more flexibility than latitude and longitude. I could use a different coordinate system if I needed to. Now we're going to set up what our projection is. With this, the CRS function. And now let's do the simplest possible variogram. We're going to say the log of zinc depends on 1. The MeUse data set involves a river, and specifically, like there's around, like right before a bend, or where there's a bend, we see a larger concentration of things where it looks like the water is hitting the shore before it turns. And here's our variogram. Now let's modify our variogram to consider the coordinates this way. And so this will be a variogram with a linear trend. And so now we can just see what we get off of this. And now we can do a directional variogram by considering direction. And so here are the angles that we are considering. And now we can set up our width and our cutoff for us very nicely. And now we can also use the fit variogram function. And this, I'm using the variogram. So here I have the variogram, and now I'm actually going to fit the model. And the model that I'm going to pick is from the VGM function, and specifically it's going to be spherical. And here's my range and my nugget. I talk about these types of models extensively in my other videos. And so here we see what we've got going on. We can also use the gstat function. This is like a huge function in this package. This function does a lot. And so here I'm just going through and setting up the model to fit it. Here I'm applying a transformation to the me-used data, and I'm specifying what projection I want. This is a good general projection for most situations, by the way. And here I can go through and we have a variogram of unprojected data using great circle distances, returning kilometers as units. And I'm just printing out that variogram here. Most of the functions of the gstat package require having spatial coordinates and data from the observations. These can be in the spatial points data frame objects, or they can actually be separate. I can have my coordinates and my data in two separate spots. I advise you to put them into a spatial points data frame if it's not too much trouble, just because you can invoke more packages that way. And you can always decouple them really easily. Now, the gmGeostats package, this acts as a bridge between composition data and spatial statistics approaches. And so the functionalities of gmGeostats are similar to those of gstat, but they are tailored towards like the compositions and fully multivariate modeling. Data in gmGeostats is organized in layers of information, which can be multivariate or univariate in nature, and each will have its own scale. The multi-layered data sets can be linked to coordinates in a spatial data frame object. And as in geostats, a geostatistical model is constructed by binding these spatial data frames with certain model parameters and certain method parameters. Several geostatistical techniques can be obtained with a systematic combination of these model and method parameters. All right, so this has been a very, very, very brief overview of the SP package, which has objects for us storing spatial data, and the geostats package, which gives us tools for geostatistical analysis of regular data, and also of the gmGeostats package, which connects composition data to spatial statistical methods. All right. Well, that's all I've got for you. Life is short. Do math.